Welcome to The Explainer. Today, we're embarking on a journey to the very edge of human knowledge. I want you to imagine computer science as this vast, extensively mapped territory. We know exactly where the safe roads are, and we definitely know where the dead ends are. But right in the middle of this map lies a massive, uncharted wilderness. It's a question so incredibly profound that solving it would literally change the world overnight. I am talking, of course, about the greatest unsolved mystery in computer science, P versus NP. Okay, let's dive right into this. Here's our syllabus for today's journey. First, decidable versus undecidable problems. Second, unpacking P versus NP. Third, the NP-complete master key. Fourth, polynomial time reductions. And finally, number 5, a quick P or NP knowledge check. All right, section 1, decidable versus undecidable problems. Before we can even start talking about how fast a computer can solve a problem, we have to ask a much more fundamental question. And that is, can it solve the problem at all? You see, there are absolute limits to computation. On one hand, we have decidable problems. These are the everyday tasks your phone or your laptop crushes constantly: sorting a list of names, finding the largest number in a dataset, or calculating a route on a map. There's a clear, step-by-step algorithm that absolutely guarantees an answer. But on the flip side, we have undecidable problems. And these aren't just, really difficult. They are mathematical brick walls. It is logically impossible for any algorithm on any computer, past, present, or future, to ever solve them. The absolute most famous of these brick walls is the halting problem, which is first proposed by the brilliant Alan Turing. The setup sounds pretty simple, right? Can you write a master program that looks at any other program and tells you if it'll eventually stop running or if it's just stuck in an infinite loop? Well, if you assume such a program actually exists, let's go ahead and call it the halt program, you immediately run into a paradox. See, you could just write a new program that asks halt what it's going to do and then deliberately does the exact opposite. If halt says it'll stop, the new program loops forever. If halt says it'll loop, the new program stops. Because of this inescapable logical contradiction, the halting problem is completely undecidable. A perfect debugging tool that catches every infinite loop, it literally cannot exist. Moving right along to section 2, unpacking P versus NP. So, leaving the impossible behind, we are now safely in the realm of decidable problems, stuff computers can actually solve. But the question shifts from can we solve it to how fast can we solve it? To understand this complexity, computer scientists focus on a very specific format. Consider the difference between decision problems and optimization problems. Optimization asks for the absolute best answer. Think, what is the absolute shortest possible route between 10 cities? Decision problems, on the other hand, just ask a simple yes or no question, like, is there a route between these 10 cities that uses at most 500 miles? Now, why do we focus strictly on the yes-no questions when studying P versus NP? Because finding the absolute best route is always at least as hard as just checking if a good enough route exists. By stripping the problem down to a simple yes or no, we isolate exactly what makes the math so difficult. Now, before we define the letters P and NP, I really want you to think about this question. Why is verifying a given solution often infinitely easier than constructing that solution from scratch? Imagine a massive 10,000-piece jigsaw puzzle. Putting that together from scratch, that takes days of grueling effort. But if someone walks up, hands you a completed puzzle and asks, hey, did I put this together correctly? You can verify the solution in seconds just by glancing at it. That massive, unbelievable difference in effort between finding an answer and checking an answer, that is the entire foundation of PVS versus NP. And here is exactly where we draw the battle lines. Class P contains problems that can be solved quickly, specifically in polynomial time, by a standard deterministic computer. These algorithms make logical, step-by-step choices. Think of sorting a list of numbers. Your computer knocks it out in a fraction of a second. Class NP, however, stands for non-deterministic polynomial time. To solve these quickly, you would need a completely theoretical computer, something with infinite parallel computing power, or a perfect guesser that magically knows the exact right path to take at every single fork in the road. In reality, without that magic computer, finding the solution to an NP problem takes an agonizingly long, non-polynomial amount of time, like exponential time. But, and this is the absolute key, if someone hands you the magic guess, you can verify if it's correct incredibly fast, in polynomial time. Let's anchor this concept with a classic example, the Hamiltonian cycle. This problem asks, in a given network of connected points, is there a path that visits every single point exactly once and returns to the start? If you have to find that answer from scratch by checking every possible combination, well, you hit a brick wall of factorial time. For a really large network, the sun would literally burn out before your computer finished checking. But if a friend hands you a map with a path already highlighted in red and claims, hey, this is the Hamiltonian cycle, you can just trace your finger along the line. Does it hit every point once? Yes. Does it go back to the start? Yes. Verifying the answer is trivial. It takes linear time. But finding it, that takes practically forever. Let's move into Section 3, the NP-complete master key. Okay, so we know P problems are relatively easy to solve, and NP problems are easy to check but seemingly impossible to solve quickly. But within the NP class itself, there's this highly exclusive club. NP-complete, or NPC problems, are the absolute hardest problems in the entire NP class. But they have this almost magical property. They are perfectly interconnected. Solving an NP-complete problem is at least as hard as solving any other problem in NP. They act like universal translators for computational complexity. If you figure out a fast polynomial time algorithm for just one single NP-complete problem, you haven't just solved that one problem, you have essentially solved them all. Let's do a little time travel back to the year 1971. This is a truly monumental year in computer science because a researcher named Stephen Cook proved something astonishing. He proved that a specific logic puzzle, known as SAT, or Boolean satisfiability, was the very first NP-complete problem. He mathematically demonstrated that every single problem in the NP class could be cleanly translated into a SAT problem. And this brilliantly illustrates the massive stakes we're dealing with here. If even one NP-complete problem could be solved in polynomial time, then all NP problems could be solved in polynomial time, meaning P equals NP. This is the ultimate domino effect. Right now, computer scientists generally believe P does not equal NP. We believe some problems are just inherently, unavoidably hard to solve. But if someone writes a fast algorithm for just one NP-complete problem, that single algorithm becomes a master key. It unlocks every single NP problem in existence, instantly collapsing the entire incredibly difficult NP class right into the easily solvable P class. Next up, Section 4, Polynomial Time Reductions. So how exactly do computer scientists actually prove that these problems are mathematically linked? How do we build this web of master keys? Well, to prove a new problem belongs to the exclusive NP-complete club, they use a strict two-step procedure. First, you've got to prove the new problem is actually in NP, meaning if someone gives you a guessed solution, you can verify it quickly in polynomial time. Second, you take an existing, already proven NP-complete problem, and you write a fast algorithm that transforms its input into your new problem's input. This transformation is what we call a polynomial time reduction. You're essentially proving that your new problem is just an existing, impossibly hard problem wearing a different disguise. It is absolutely incredible to see this chain reaction in practice. Remember that SAT problem from 1971? Researchers quickly showed that a version of it, called 3SAT, can be mathematically transformed or reduced into the clique problem, which involves finding fully connected clusters in a network. Then they proved the clique problem can be reduced into the vertex cover problem. And guess what? All of these tie right back to our old friend, the Hamiltonian cycle. It's this intricate, beautiful web of complexity. Because they all reduce to one another, finding a fast solution to any of them means finding a fast solution to all of them. Let's actually look a bit closer at the vertex cover problem as a practical reduction example. The question is, in a given graph, is there a small subset of nodes, let's call it K nodes, that touches every single line or edge in the entire network? Because we know we can perfectly transform the notoriously difficult clique problem into this vertex cover problem quickly, logic dictates a pretty profound truth. If we can't solve the clique problem fast, we absolutely cannot solve the vertex cover problem fast either. They share the exact same computational DNA. All right, Section 5, the P or NP knowledge check. We've covered a ton of ground today, from the absolute limits of computing to the interconnected webs of NP completeness. So it's time to put on your computer science hats and test the concepts we've built together. Here's your first challenge. Look at these two problems. Finding the shortest path between 2 points versus finding a Hamiltonian path that visits every single point exactly once. Which one belongs to the fast, easily solvable class P, and which one belongs to the frustratingly slow class NP? Take a second to think about it. Got it? Well, if you said shortest path is in class P and the Hamiltonian path is in class NP, you are absolutely right. Your phone's GPS solves shortest path in milliseconds, but as we learned earlier, calculating a Hamiltonian route from scratch requires checking a massive exponential number of paths. Okay, let's try just one more. Eulerian path versus longest path.
An Eulerian path asks you to trace a route that uses every single line or edge exactly once. The longest path simply asks for the absolute longest route between 2 points without ever repeating nodes. So which is the easily solvable one and which is the computational nightmare? Believe it or not, finding an Eulerian path is actually quite easy and belongs firmly in Class P. There are really fast deterministic rules for it. But finding the longest path? That jumps straight off a cliff right into the exponential abyss of Class NP. It's incredibly hard to calculate from scratch, but very, very easy to verify if someone hands you the answer.
And this brings us to our final thought. I really want you to truly consider the weight of this question. If cracking just one NP-complete problem proves that P equals NP, how would finding that single algorithm alter the limits of human computation forever? Well, if P equals NP, the encryption protecting our bank accounts and private messages, that would collapse overnight because breaking codes is fundamentally an NP problem. But on the flip side, we could instantly optimize global supply chains, we could cure diseases by effortlessly folding proteins, and solve logistics problems that currently seem downright impossible. The person who finds that master key won't just solve a math puzzle, they will rewrite the rules of what humanity can achieve. Thank you so much for joining me on this explainer, and keep questioning the limits of the possible.